Okay, so today we're very happy to have Xueda Wen from Harvard and CU Boulder, who's going to be telling us about Floquet CFTs and conformal cooling.
Yeah, thank you, Bruno, for the introduction. Thank everyone for coming. Today, I'm going to introduce our recent story on something called conformal cooling. So this is mainly based on the recent work with Ruihua Fan, who is a graduate student at Harvard in Ashland group. Let me start from the outline. I will first give some motivation for this work, and then I will introduce a family of exactly solvable driven CFT that have interesting phase diagram, and then we will apply this setup to finite temperature, and we found that it can be used at quantum cooling. Okay, so the introduction. First, we know that in quantum many-body physics, there can be a very rich physics when we have more and more particles. For example, if we know very well about the property of a single water molecule, it doesn't mean we can understand the phase diagram for a cup of water very well, right? And similarly, in non-equilibrium physics, so even if we know the phase diagram very well, it doesn't mean we can understand everything when the system is out of equilibrium. For example, if you put your water in a disk and you heat it, there can be some very interesting patterns which are called Rayleigh-Bernard convection cells. These are some non-equilibrium patterns. Okay, what I mean is that when we study the non-equilibrium physics, there can be something new which are not existing in the equilibrium physics. Okay, so the motivation of this talk is to study some interesting thing in non-equilibrium physics. Okay, although it is interesting, but we know there are many challenges in non-equilibrium physics. For example, when the system is far from equilibrium, there can be lots of excitations. Okay, there can be lots of excitations. The entanglement can be very large. So we know that when the entanglement, when there is much entanglement, there is no efficient numerical method. For example, in quantum many-body physics, for example, in one-dimensional system, people use the matrix product state a numerical method. This method works very well when the entanglement is not large. For example, when there is area law entanglement, it works very well. But now, if the system is far from equilibrium, the entanglement can be like a volume law and so on. Then the numerical method doesn't work well. So in this talk, instead of studying things numerically, we introduce exactly solvable setup in one-dimensional CFT. So we found something interesting with the following features. First, our setup is universal, which means the result should be independent of the concrete model on the concrete CFTs. We should have some universal feature. And we also hope it is non-trivial, which means when you drive the system, if nothing interesting happens, then it's not interesting. We hope there can be an interesting phase diagram. Okay, and we also hope it can be useful. For example, our setup can be used to control, to manipulate the quantum entanglement and also the thermal entropy. Okay, I will introduce the details in the following slide. Okay, so the idea before we introduce the concrete setup, the idea is really from our daily life experience. It is from swing. So I think everyone knows how to swing in the playground. So in general, we need to deform our body in time, okay? And roughly, there can be two different phases. I call it stable and unstable. Okay, unstable means when you do the swing, you can swing higher and higher. Your energy grows in time. It's not, we are absorbing energy, so it's not stable. For stable phase, I mean, if we don't play very well, we simply oscillate in some very small amplitude. The energy doesn't grow in time. It is stable. So how to understand this feature in a quantitative way? Let's consider a very simple harmonic oscillator. Okay, a zero-dimensional harmonic oscillator. This is a quantum mechanics problem. Here we start from a Hamiltonian for a harmonic oscillator. So now here the oscillating frequency is dependent on time. Okay, this is a time-dependent oscillating harmonic oscillator. So if you look at this Hamiltonian carefully, you can find that this Hamiltonian is actually generated by SL2R algebra. There are three generators which span this SL2R algebra. Okay, and how do we study this problem? The one simple way is to study the operator evolution. What I mean by operator evolution is.
Sorry, what do you mean when you say if there's an SL2R? What's the SL2R?
Oh, SL2R means that we can write down three generators. Their
I
communication.
know what the group SL2R is. What is it in this problem?
What is
What is it in the context of this problem?
Oh, very good. So I mean, because now the Hamiltonian is time dependent. Okay, so you can find this Hamiltonian is generated by three generators. For example, we can write down there is G1 equals T squared plus X squared. G2 is T squared minus X squared, and G3 is like Px plus Xp. So this Hamiltonian at a different time, they don't commute, but they are generated by the three generators. Then the three generators span the SL2R algebra.
Are you saying that the Casimir of SL2R is the Hamiltonian?
No, I don't think he's saying that. That's what I was asking.
The Hamiltonians is a linear combination.
It's a linear combination of the
Time
three
dependent
generators.
linear
okay.
combination of these three.
Yes, yes. And the Hamiltonian exactly is a linear combination of the three generators. Sorry, I forgot some coefficient. Okay, this is what I mean by SL2R algebra. So when we study the operator evolution in the phase space, we can find that the X and P will evolve in time. In this phase space. It is determined by a 2x2 matrix, which is SL2R matrix. So in this problem, we can tune the driving frequency omega here. We can also tune the driving amplitude H here. As we tune these parameters, we can find this operator evolution have two different behaviors.
Is that formula for omega of t supposed to be a model for a real swing? How did you cook up this formula for omega of t? Why are you considering that particular formula?
Oh, okay. For example, if this one is constant, it simply means the harmonic oscillator has a fixed frequency. But now, as we deform our center of mass, this omega will depend on time.
Well, it depends on time, but why that particular time dependence?
Oh, this one, I mean, imagine we can tune our center of mass in this in this way. Sure, you can tune your center of mass in some other time-dependent way. Yeah.
I have a question. So it seems like you have omega t and the right side also has an omega t. Like the h cos omega t, is this some sort of like recursive definition? Like what is the omega in there? Is it omega naught or is it omega of t?
Oh, this is
Some other constant.
Is it omega naught?
this is some constant. Here, this omega.
I think he's worried that that omega is the same as the symbol.
Oh, sorry, my bad. Let me write this omega as omega 1.
Okay.
Okay.
So there's three couplings there, like three parameters.
Oh, no. There are only two parameters, h and this omega 1.
I see. Okay.
And only two parameters. So this is why later I will show a phase diagram. We can only tune
Okay. Okay.
omega 1 and h. Okay. Yeah. So depending on the two parameters here, the operator evolution can have two different behaviors. In one case, the operator evolution will simply oscillate along a circle, and the total energy x squared plus p squared doesn't grow.
However, right
However,
now drawing classical pictures, right? You're using a quantum language, but those are classical trajectories.
yeah. I mean, this is operator in Heisenberg picture. Yeah. And as we tune some other parameters, h and omega, x and p they can flow to infinity. If you check the energy, it will grow in time. So this is what we mean by stable and unstable. Okay.
What do you mean by the energy?
Oh, here by energy, I simply define it as x squared plus p squared as a function of time. This is a wave function. So we define the quantity as a total energy as a function of time.
There's no dissipation in this system.
Huh?
There's no dissipation in this system.
No dissipation. Yeah. Here I didn't introduce any dissipation.
But there's
Right.
also no real notion of energy.
Yeah, there's no conserved energy.
Yeah, no conserved energy. Exactly.
There is discrete time translation invariance, right?
Oh, here we can choose some continuous time. That's all. I mean,
I think Son means that you have an omega, the time dependence is periodic, so there's some quasi energy.
oh, 2 pi over omega is time. Yeah. Yeah, but here what I mean by energy growth is simply this: if the driving frequency is independent of time, it has well-defined energy in this way. Now we simply make this driving frequency and time dependent. We study the same quantity in time and say if this energy grows in time or not. Yeah. So based on this operator evolution, we can have two different phases. One is stable and the other is unstable. Okay. This is simply some picture, a very simple picture on how to play swing. Okay. But the topic today is we want to study the one-dimensional CFT. Okay, but the question is how to play swing in the one-dimensional CFT. So imagine that at the very beginning, we are given a one-dimensional system where the Hamiltonian density is homogeneous. It's homogeneous in space. Okay, we have for example, here the lattice model. There is translation invariant in space. Okay, now to play swing in the second step, we will deform the system inhomogeneously in space. What does this mean? This means we can write down a new Hamiltonian, which we call H1. In this new Hamiltonian, we tune the Hamiltonian density as a function of a space. Okay, if you compare the two Hamiltonians, H0 and H1, for H1, we simply modify the Hamiltonian density by a function, a real function, fx. So which is depicted here. We tune the Hamiltonian density in space. So this step is to mimic our deformation of body in pumping a swing. Okay, that's it. This is simply the setup. Next, we will do the driving. What we mean by drive the system periodically in time is this. We will imagine we start from some initial state. Then we will use Hamiltonian H1 for some time evolution, and then we switch Hamiltonian H1 to H0 for another finite time. Then we repeat this procedure in time. Okay, this is what we mean by drive the system periodically in time. Okay, but the question is, how is this setup related to swing? Okay, we can understand this relation in the following slide. So first, we want to emphasize when we deform the Hamiltonian density, then we can have some Fourier component of the deformation. For example, here T is the stress tensor in a conformal field theory. If you look at the Fourier component of the deformation, we will have we define some operator which we call Ln. So these operators are nothing. These operators generate nothing but the Virasora algebra in one-dimensional CFT. These operators satisfy the commutation relation here. This is the well-known Virasora algebra. Okay, there are infinitely many generators in this Virasora algebra. However, within this Virasora algebra, there is some finite dimensional the SL2R algebra, which are generated by 3 generators, L0, Ln, and L minus n. Within this very big algebra, there's a small and finite algebra, which is SL2R algebra. So the question is how to realize these 3 generators in our setup. It's very easy. We can simply deform our Hamiltonian density by this function. So there's a cosine 2 pi n x over L. Here n is some integer, and A, B, C are some random arbitrary constant. So if we deform our 1D system,
So if n is not equal to 1, is it still SL2R algebra?
yes. If n is not equal to 1, maybe you ask there are some constant here, right? Yeah. So, but now if there are only L0 and L plus minus n, there are only these 3 generators involved in this question. You can shift the Ln and minus n by some constant. So this piece will vanish. I mean, it is still SL2R algebra. Yeah.
So it looks like you shifted by a trace though, which would make it not traceless anymore. SL2R is traceless, right?
I mean, you can still, by redefining your L 0 and L plus minus n, so they will satisfy, I mean, the
L0?
L0 is always there.
L0 by a constant?
Shift Ln or L0, I forgot, but I mean, this is only some constant term, right? So maybe L0.
L0.
I think it's not shift L0 because if you put Ln and L minus n here, this term doesn't vanish, right?
You get L0 on the right side.
Can you do that?
You can't remove the central term with a shift.
Sorry.
No, you might be able to remove it if you delete all the other charges other than L plus minus n.
But isn't the problem that L plus n commuted with L minus n will always give you the central term? Yeah, it doesn't matter what you add to the L.
Plus L0, right? So like the idea is to redefine L0 so that that central term is absorbed into L0.
Oh, you say, oh, I see, yeah.
Yeah, I mean, if
Yeah, okay.
at the same time, if there are other L minus M, then we cannot do this. But
Yeah.
if in the whole driving process, these are the only three generators. You can redefine them by shifting a constant. This is okay. But if at the same time, if you have other L, M, L, K, you cannot do this. You cannot always it's not closed.
So
Closed.
I guess the statement is for SL2R, there is no central extension.
Yeah.
The algebra. And that's what you restricted.
Yeah, so what I mean here by SL2R is up to this constant, constant. You can absorb it by redefining generator. Okay. Once we do this, now we have the SL2R algebra. It has the same algebra as the swing, right? Then we expect that there can be two different phases in this driving problem. Okay. Okay, so how do we study this problem? So usually when we calculate the non-equilibrium time evolution, we are interested in the correlation function, multi-point correlation function. Again, here this O1, O2, they are defined in this Heisenberg picture. Here, U, UT, and U dagger are the unitary time evolution operator, which correspond to the driving. Okay, so roughly speaking, these operators, as we drive this operator, as we drive the system, these operators will evolve in the two-dimensional space-time. Now we will study how these operators evolve on the two-dimensional space-time. To give a very concrete example, imagine we start the driving from the ground state of the undeformed Hamiltonian. Okay. Then the relevant path integral is as follows. If the initial state is the ground state of the undeformed Hamiltonian, the total system is of length L. Okay, this is in this W plane. We have space in this direction and imaginary time in this direction. It goes from minus infinity to positive infinity. So when we study this operator evolution, it's convenient to first do a conformal mapping by mapping this W plane to some V plane. Map this plane to some unlayered manifold. Okay, then for this SL2 deformed Hamiltonian, what we found is very simple. The operator, as we drive the system, this operator will simply move along a circle. I mean, the circle, if you look at only at one layer, it's a circle. This trajectory is a circle. So this operator will evolve from the old coordinate ZZ bar to some new coordinate Z new and ZZ new bar. So this operator evolution is determined, I mean, Z new here, the new location here is related to the old location by a 2x2 matrix. This is called the Mobius transformation. So this 2x2 matrix is a SU1, matrix. It is isomorphic to SL2R matrix.
So your system doesn't preserve conformal symmetry anymore, right? Why are we doing this fancy conformal transformation?
Oh, actually, you can consider this problem as a CFT with curved space-time metric. We simply change the metric, actually.
We change the metric.
Yeah, it's always a CFT, actually. Yeah, but with curved space-time. Yeah, this is why we can study this problem within the CFT framework. If the system is no longer a CFT, I don't know how to study.
But you have some exponentiated operator that is
Exactly.
that has some
Exactly.
scales and things in it, right? So why do you still have conformal symmetry?
Oh, the question is very simple. So if you have an operator O, So the unitary time evolution is something like, for example, E2 minus, right? This is L0 plus Ln and plus L minus n. There is some coefficient. So
There's some time dependent and position dependent.
yeah. So basically, the time evolution is unitary operator here. You know, we always have some other Varasora generator. Then there's a U-dagger here. We simply need to figure out how this operator evolve under this unitary time evolution. Yeah, this is
No, but it's not just e to the t there, right? Isn't it a function that turns on and off in t?
yeah. So this is a very this is not the exact. I mean, it's a function, some function of t, but
And not even a smooth function.
there's a two-step. There's a step function. Yeah. So, but roughly this part is the most important. Yeah. Okay. So the setup is very simple. Okay. As Clay mentioned, so when you drive the system for a single step, it is described by a single 2x2 matrix. Now, if you drive the system by a n step, we will have a multiplication of n 2x2 matrix. So this relation determines how the operator evolves in time. So we can have n the product of n matrix. So this is a non-equilibrium problem, but essentially we are actually performing the conformal transformation in time. That's why the problem can be analytically solved. Okay. Then you may want to ask, okay, what is the phase diagram? How do we under the phase diagram in parallel with the swing problem, right? Okay, the phase diagram can be determined in a very, very simple way. We simply, as we drive the system with the product of n 2x2 matrix, we simply need to study the trace, the absolute value of this trace of this product of 2x2 matrix. Depending on this value is smaller or bigger than 2, we can have two different phases. We can have one heating phase and one non-heating phase with some phase transition. Let me give more details and follows. So the meaning of this phase diagram is determined by the operator evolution. For example, if we are in this non-heating phase, then the operator evolution will be determined by some elliptic Mobius transformation. The operator will simply oscillate along a circle. So everything will oscillate along a circle. Then this means the system can go back to its initial state. This means the system is stable. This is similar to the swing, the energy, the operator simply oscillate along a circle. However, in this heating phase, the operator will no longer oscillate along the circle. It will flow from some unstable fixed point to some stable fixed point. It will never come back to its initial location. This means the system can never go back to the initial condition. This means something interesting may happen. And in between the two behaviors, there's a parabolic feature of the operator evolution. There's a single fixed point. It is not stable and not, it's like the operator can flow from this side and back to this the single fixed point. Okay, this is simply some mathematical picture, but what are the physical features in different phases? Let me give you a very concrete example. So here we consider two Hamiltonians H0, which is a uniform Hamiltonian, and another Hamiltonian H1, which is we simply deform the Hamiltonian density by a cosine function with a wavelength small l. The capital L is the total length of the 1D system. So there are n integer number of the wavelengths within the deformation. Okay, that's it. Now when we drive the system, the only parameters we can tune are the time t1 and t0. Okay, t1 and t0. Then, okay, now what we can plot in the we can change the time t1 here and the t0 here. We can get some phase diagram. This phase diagram is simply determined by the operator evolution introduced in the previous slide. Okay, we found some two different phases. In this non-heating phase, nothing is interesting. Everything will oscillate in time. But in this heating phase, if you study the energy density evolution, so what I show here, this direction is the space direction, and this direction is driving the number. So here n is the number of driving. We drive the system with 1 step, 2 step, 3 step, and so on. As we drive the system in time, we can find that the energy density will be accumulated at some very special point. Okay, so the location of this peak is determined by the operator evolution, by the fixed point I introduced in the previous slide. This is some conformal field theory calculation, and we also do the simulation lattice model. This is the lattice free Fermi lattice model. You can find the agree very well. So this is some feature in this heating phase, where the energy, the total energy of the system will grow in time. Okay. Yeah. Here, the location of the energy density peak is determined by the location of the fixed point in the operator evolution. And later, in another work,
Sorry, can you just elaborate on that last point? So we have some SL2R matrix, which is classified into one of those types. And how is that classification into types telling you which point in space?
Oh, very good. So, okay, for example, here in this plot, you can find that there are four peaks, right? This is because in the deformation, I choose two wavelengths in the deformation. Okay, then for two wavelengths, if
Sorry,
you
in which in the exponents there?
oh yeah, sorry. When I write down the Hamiltonian H1, we deform the system by some function. Yeah, this is the total system is a capital L. The wavelength of the deformation is small l. In this calculation, we choose two wavelengths in the deformation. This is why we have 4 energy peak, because two are chiral density energy peak, and the other 2 are anti-chiral energy density peaks. If you deform the system by an arbitrary number n wavelengths, you will have 2n energy density peak. Yeah, 2n energy density peak. So the location of this peak is determined by the fixed point, in the operator evolution. Yeah.
Sorry, I just got myself confused. Which 2D CFT were you computing it?
Oh yeah, this is for arbitrary 2D CFT.
Okay, so it doesn't matter.
It doesn't matter. Yeah, this is
We're
why
not even using the operator spectrum, it just uses the SL2R eigenvalues of that,
Right.
of that matrix. Yeah.
When you're saying exact calculation of the field theory, so the details made no difference. It made no difference. You just needed conformal symmetry.
Yeah, the only thing we need is the Virasora algebra. So we don't use any other kind of thing. Yeah, but in this concrete calculation, we use the free Fermi CFT, right? Because we need to compare it with the free Fermi lattice calculation. But the whole story is independent of what kind of CFT consider. Yeah, this is my motivation for this slide. For this slide, another group they use a very different model called the XXZ model. This is compact free boson CFT. They compare their numerical result and the CFT calculation. They found that also the very good agreement. Yeah, it's not a very good agreement because their lattice size is very small. It's like 80 spins. Yeah, but my point is the result is really independent of the concrete lattice model and CFT.
Okay, just to check again, the choice of little n in your perturbation is affecting which aspect again of the?
Oh, very good. The n. So if you have a system of total length capital L, you can deform your system by wavelength small l. My definition of n is capital L over small l. That's it. Yeah, here you can only observe two peaks because they choose n equals 1. Yeah, their calculation. Yeah, this is a feature of the energy density evolution. So we are also interested in the quantum entanglement evolution. For example, we want to ask if you study the entanglement between the left half and the right half, what is the entanglement? Okay, we use the entanglement entropy. What we found is very interesting. In this non-heating phase, the entanglement entropy for the half system simply oscillates in time. Okay, this is as expected because the operator simply oscillates in time. However, if we are in the heating phase, the entanglement entropy will grow linearly in time. And at the phase transition here, the entanglement entropy will grow as log t. Okay, and the coefficient of this log t is central charge over 3.
Are all these dependence, you mean a coefficient in front of log L or what? So the scaling of should be a log, right?
You mean with this one?
I mean the entanglement entropy, the quantity.
Oh yeah. I totally agree. Yeah, what I mean is this. This is a finite system. If you study the entanglement entropy in the ground state, it grows as a log L of the subsystem size. But now we are interested in the time evolution based on this value. You have a log L at the very beginning, but as you drive the system, it will grow linearly.
I see.
Now we already removed the initial log L value. Based on this, it will grow linearly in time.
I see. So it's kind of a coefficient has this dependence and time central charge and.
Oh no. It is the initial is log L plus some linear growth of time.
Oh, I see.
Yeah.
You mean I see. The sub-leading term has dependence, but the leading term is independent of the driving.
Yeah. This is a leading term in the long time driving limit. Right? This is your initial entanglement.
Is alpha necessarily independent of the length?
Oh, this alpha it depends on your driving Hamiltonian H0, H1, and also your time T0, T1.
Right. But does it depend on L, the system size?
It doesn't.
Region.
It doesn't depend.
Okay.
Yeah. It only depends on the driving.
I see.
Yeah.
So here you had you turned on and turned off with a step function.
Yeah.
If you smoothed it, would it matter much?
It doesn't matter. Another group they studied this smooth deformation. They found the same feature.
What is this omega in the non-heating phase?
Oh, you mean this omega, right? Yeah. This omega is very, very interesting. For example, when you drive the system, very, very quickly, which means you are in the high frequency limit, this omega is independent of your T0 and T1. It only depends on your deformation length, actually. This is something interesting.
You mean like it depends on n, but it doesn't depend on?
This omega will only depend on this wavelength deformation. it is independent of your how quickly or how slowly you drive your system.
It's one of the eigenvalues of the elliptic matrix.
Eigenvalue. I don't remember how it's related to the eigenvalue. Sure, they are related, but I'm not sure if it's exactly the same thing. Yeah, because everything is determined by the operator evolution. So that 2x2 matrix contains all the information in this time evolution. Yeah. Okay. Before I move forward, there's one interesting thing I want to emphasize. So in equilibrium physics, we are interested in the universality class, how the feature behave as we go as we are close to the phase transition. Here, what we found as we, for example, here as we cross this phase transition, we can study how this linear growth behaves and how the oscillation period change as we are close to the phase transition. What we found is very interesting. If we go from the heating phase to the phase transition, we change the parameter T close to this T star. T star is where a phase transition happens. So the rate of the linear growth will, depending on this external parameter, scaling behavior in this way. Similarly, if we go from the non-heating phase to the phase transition, the oscillating period will diverge in this way. So the exponents here are really independent of what kind of a CFT they are considering. So it's some super universal feature for the critical exponents. This is simply some observation. Oh, I found I'm moving very slowly. Okay. One more feature I want to emphasize. So why, you may want to ask why the entanglement entropy grows linearly in the heating phase. There is actually a very intuitive picture. So as we drive the system in the heating phase, first there will be some energy density peaks as we introduced just now. So in this process, as we mentioned, there are stable fixed point and unstable fixed point. For this unstable fixed point, some EPR pairs will be splitted with one member moving to the left peak and the other member moving to the right peak. These two peaks are entangled with each other, and this entanglement grow linearly in time. So this means as we drive the system, we are actually pumping some entangled pairs and split them to different locations in space. So we call it something like an entanglement pump. But this is some intuitive picture for the linear growth of entanglement entropy. So later we study this periodical driving. We also study random driving and also in some quasi-periodical driving. This problem can be mapped to some crystal, quasi-crystal, and Anderson localization in our solid state physics. There is some mapping. Okay, I will move quickly to the cooling part. So just now we have introduced the basic setup of the Wen-Floquet CFT. We want to use this setup as a cooling. So what we mean is this: if your system is initially prepared at a finite temperature, so there is both a quantum entanglement and also the thermal, the classical correlation. So when we drive the system in the heating phase, what we found is that the thermal entropy, for example, the thermal entropy here can be pumped to the energy density peaks. So if you look at the region here, you can find that the temperature will go from finite temperature to zero temperature exponentially fast in time. So we will give give you some details for this cooling process.
Isn't temperature kind of an equilibrium notion? What are we exactly talking about here?
Yeah. Exactly. So in the next two slides, I will introduce what do I mean by studying the temperature in this region. After two slides, I can answer your question. So before I go into the next slide, I will mention some similar idea were recently considered in some other system in some gapped codatum system, but in a single quantum quench. It's also considered in some moving mirror problem. The setup are different, but the idea is quite related. So roughly, we are moving the thermal entropy from one place to the other place. So then we can use this to realize the cooling. Okay, let me go to the concrete setup. So basically, the system is initially prepared at some finite temperature, which is the thermal state. There's the inverse temperature beta here. And when we do the driving, we introduce some finite wavelength. So in this problem, okay, I want to mention here, we consider an infinite long 1D system. So the finite temperature beta and the wavelength L, they are the only two length scales in this problem. Okay, we consider infinite long system. Okay, now if you study the energy density, now let's study the energy density in this region between the two energy density peaks. Before we drive the system, okay, the energy density it depends on the temperature, right? This is the well-known result. It is proportional to T squared. T is the temperature. Now, as we drive the system, we can find that this energy density will decrease to the Casimir ground state value. So this is some negative value. So in this plot, the red dashed line is the CFT calculation. We also do the lattice simulation, which is some green line. Maybe you cannot see it clearly. They agree very well. So we can say the energy density goes from the thermal value to the ground state Casimir value in time. So it decreases.
Sorry, I'm confused. That's what do you mean when you say that's the ground state value? I thought the Casimir energy was that you're talking about that refers to as for a system on a circle.
Oh, very good. So again, very good question. So what I mean, why? Yeah, okay. The setup is that we consider an infinitely a long system, but this value is the ground state value of the CFT on a circle of length small l.
Right.
Yeah.
So why did we get that?
Yeah, this is simply why do we get this is a okay. Let me make it clear what I mean by
why did you call it Casimir energy? Casimir energy means finite spatial size.
Yeah.
Right. So
yeah. So my claim is very simple. When we do this cooling, the final wave function or the final physical observables are the same as the observables for a finite CFT of length L at 0 temperature. Yeah, I will tell you more detail in later when we study the reduced density matrix. So your initial state
L is the distance between the two spikes.
Yeah, yes, exactly. Yeah, this is some very interesting feature. The cooling is not cooling down to the ground state of an infinite system, but it is cooling down to the ground state of a finite CFT. I mean, or circle L. This L is exactly the distance between the two peaks.
Is there any communication between the regions separated by an intermediate spike?
Oh, very good question. Currently I don't know the answer. It's you need to study the mutual information in this region and this region, right? We haven't done this calculation. Yeah, I don't know the answer. This is yeah, my collaborator also asked me this question, but we don't know the answer now. Okay, we can see the cooling effect in this region, but the total energy of the system still grows in time. This is like you know, in our refrigerator. Inside of the refrigerator, the temperature is low, but as a whole, because we are inputting power, right? So the whole room is the energy is growing. So it's similar here. Although this region is cooling down to some ground state value, but the total system is absorbing energy exponentially fast in time. Okay, this is energy. Similarly, if you study the von Neumann entropy, in this subsystem, here we have 3 different lines because we can do 3 different initial temperature, As we drive the system in time, no matter what is your initial temperature, finally the von Neumann entropy in the cooling region will decrease to the ground state value of a CFT, again on a circle of length L. Okay, and yeah, this is what happened in this cooling region. If you study the von Neumann entropy in this heating region, it will grow linearly in time. Okay, till now I simply show you some concrete quantity, the energy, the entropy. Okay, to convince ourselves more completely, so we study the reduced density matrix. So the whole information of the subsystem A is contained in this reduced density matrix rho A. Okay, so we know that the reduced density matrix can be equivalently expressed as the entanglement Hamiltonian. Entanglement Hamiltonian is defined as the minus log of reduced density matrix. So in conformal field theory, a nice property is this. This entanglement Hamiltonian is simply a function of the local physical Hamiltonian density with some modification, which we call it a local temperature. As we drive the system, at the very beginning, the reduced density matrix is nothing but the thermal density matrix. It only depends on the temperature beta. As we drive the system in time, so this local temperature here will evolve in this way. Finally, it will approach to this ground state value. So what I mean is very simple. If you study the reduced density matrix for your cooling region, it will evolve from a thermal value to some ground state reduced density matrix. So this is how we define temperature. You simply study everything in your reduced density matrix and study how your entanglement Hamiltonian evolve in time. We found that the entanglement Hamiltonian will evolve from a thermal one to the zero temperature one. This is how we define the temperature. We define it through the reduced density matrix. Okay, once we have this result, now we are confident. Indeed, we are realizing. Yeah.
Is there a reason why at like intermediate time steps the evolution is sort of achiral?
Oh, very good. It's not symmetric, right? This is because we only plotted the chiral part.
Oh, I see.
There's the anti-chiral part. We haven't. If we consider both, it will be symmetric. Yeah, that's a very good observation. Yeah. Okay. So this is the feature of the entanglement Hamiltonian in the cooling region. I think maybe you want to ask what happened if we study the reduced density matrix for this heating region. So we also calculated the entanglement Hamiltonian. What we found it is quite different from the cooling region. We can find that there are some dips. So this location correspond to the location of the energy density peak. So if this value is smaller and smaller, this means the effective temperature here is higher and higher. Why the temperature here is higher and higher? Because as we drive the system, this peak is highly entangled with the neighboring peak. This super high temperature is because of this increasing entanglement between the two peaks. This is why we see some dips here in this heating region. Okay, this is simply the conformal field theory result. We want to compare it with the lattice model calculation. Again, but in lattice model calculation, it's very hard to calculate the entanglement Hamiltonian directly because you need really high precision of your computer. But here we compare the entanglement spectrum, which is the spectrum of the entanglement Hamiltonian. In particular, only the low energy part of this entanglement spectrum is important for the entanglement property. So on the right, we compare the red dashed line is the CFT result for the entanglement spectrum in the cooling region and the heating region. And the green dots are the lattice result. We compare the field theory and the lattice calculation. They really agree with each other. Okay, so that's it. So let me give a summary of the slide here. So we start from a very simple time-dependent driving of the CFT. We can solve this problem. There can be two different phases depending on your driving. In particular, in this heating phase, we can apply it to the system which is initially prepared at finite temperature. It can realize the conformal cooling. There's some cooling region where the effective temperature can be decreased to the zero temperature exponentially fast. So the whole dynamics can be solved analytically. That's it. Yeah. Thank you for your attention. Yeah.
So if I understood correctly, you have a particular solvable model where you can get this kind of phase diagram and this heating and non-heating regions. How stable is it? Like if you, I don't know, somehow perturb it a little bit, the type of.
Yeah. I want to say this heating phase is not stable. In the following sense, for example, here we have if you break the integrability of the CFT, sure, this will vanish. But even if you preserve the integrability property, for example, here if you introduce some noise in this driving, we use Hamiltonian H1 for T1 and Hamiltonian H0 for T0. If you introduce some small fluctuations in your time T1, T0, for example, so this heating phase will also vanish. But there is always some time scale. I mean, for your perturbation stress. Within this time scale, it has a heating feature, but in the very long time limit compared to the perturbation stress, this is not stable.
Do you have some intuitive picture for why you get a non-heating phase in this system? Maybe you've said that. Like what's special about it? Oh,
what is special for the non-heating phase? There are several ways. One way is if you study the operator evolution, the operator will simply oscillate in the system, so everything will oscillate. You can also consider this question in the Fock space. I mean, if you look at the eigenvalue and in your initial Hamiltonian, when you do this driving, the system will simply only the very low, several low exciting states will be occupied, and they will simply oscillate there. However, for this heating phase, I mean in the Fock space, the system will evolve to higher and higher energy levels. Yeah, I'm not sure if there's a good understanding. Oh, yeah, maybe let me say it this way. So SL2R group, it is a non-compact group. Let me say it this way. How generally can we say about this phase diagram? My point is this: if you give me a system, as long as there is SL2R algebra, if you're in your non-equilibrium dynamics, if only the compact subgroup come in, if only the compact subgroup come in, the system will be in the non-heating phase because everything will oscillate. If some non-compact subgroup comes in your time evolution, it will flow to some, there will be some heating phase. So this is how we have two different phases in the quantum mechanical problem. So I think in general, you can also write down some gapped system where if you have some nice SL2R algebra, you can also do this time evolution. You can have similar thing. Yeah. This compact and non-compact thing is important here. Yeah.
About the super universality of your critical exponents, should I understand the reason that they don't depend on the specific universality class is just because the driving Hamiltonian that you choose is just entirely determined by the Virasoro algebra?
Yeah, I think so.
So there's any specific information about the CFT does not show up in any way.
Right. So yeah, I think this is the reason.
I see.
Only Virasoro algebra, which is therefore arbitrary to the CFT. Yeah.
Okay.
The global conformal case is not interesting, presumably, n equal 1. Because it's the entire size of the system.
For n equals 1, if you start from a ground state, nothing interesting. Yeah, but if you start from some excited state, there is interesting thing.
There is something, okay.
Yeah, there is something. Yeah.
For n equals 1, don't you still get these two energy peaks?
Yeah, the reason is this, for n equals 1, H0 and H1, they will share the same ground state.
Oh, right.
This is why I claim if you start from some excited state, which is not the eigenstate of the H1 Hamiltonian, there is an interesting thing, and there are two peaks. Yeah.
So have you tried extending to higher dimension?
Oh, very good. I believe, in higher dimensional CFT, there are also SL2R algebra. I believe the similar phase, there can still be two different phase, heating and non-heating. The reason we focus on 1D is we want to solve it exactly. We use the Virasoro conformal mapping to solve the
I think that if you just use the SL2R in higher dimensions, you could also solve it exactly.
Maybe I don't know.
Yeah.
Yeah. The point is, as long as you only use SL2R, the interesting phase diagram will also appear. So, but I don't know how to solve it.
We can talk after this.
Yeah.
Let's thank the speaker again.